Biologically relevant, very good. Okay, what else?
Conversion.
What's that?
Conversion rate.
Conversion rate, yes. And more than conversion rate, uptake rate can also play a role. We didn't talk about it in lecture, but challenges with glutamine as well is that the uptake is known to be fairly slow into cells via the transport. So yeah, you kind of have to sort of trace like all the way through, blood distribution, extravasation, cellular uptake, all those things. You got to sort of keep in mind, knowing of course where your site of reaction is. Okay, so that's two. What's the third one that we could put on the biological one?
Not toxic.
What's that?
Not toxic.
That's right. Yeah, not toxic. And particularly at, around what concentration, more or less. Like nanomole, micromole, millimole. Yeah. In fact, tens to hundreds of millimole. So, yeah, very concentrated. I mean, relatively speaking. Yep. Okay, good. Okay, how about the chemical side? What are things we can think of that are good for us? There were 4 that we listed. Let's see. Stabilities, yep, very good. That of course depends on your formulation, in part. But, okay, what else? Long T1, excellent. What else? Enough chemical shift, excellent. And there's one more.
High concentration.
High concentration. Very good. Yeah, that's, I suppose we boil it down to that. That's good. Did we put anything else here? No. That's great. That's fantastic. Okay, cool. Oh, awesome. Thank you. Again, I guess, we showed this in the lecture, but if you want to pass this around, again, this is just, sort of see what the radical looks like. It's important to notice as well that it's a large compound, and it's somewhat hydrophobic, which is why those R groups that we talked about that tune the solubility are so important. And by the way, that stuff is, I think it's $3,000. Bless you. It's $3,000, I think, for 200 milligrams. When we get the OX63, I think it's a little cheaper for the trial, but yeah. So anyway, that's that. So let's see, what else was here? Okay, well, Kong's timing is good. We talked a lot about glassing and assessing glassing, and I was sort of, coy about it, and was like, well, you gotta wait until we get to the lab to see it, but then I said it involves liquid nitrogen. Well, here's the liquid nitrogen. Even still, so this is probably the most fun we're gonna have today. So, and actually this goes very well with Manushka's question. You have to remember that with the polarizer, everything takes place, as far as your compound and your prep is concerned, your formulation, only liquid helium's in the picture. It's sitting in a liquid helium bath at that 1.4 Kelvin. Liquid nitrogen, while it's in the polarizer, never comes in contact with your compound at all, or the formulation. However, liquid nitrogen is a nice, cheap, and easy, and fairly reliable method that we've used to assess the glassing. So, it's it's not quite as cold as liquid helium, but it freezes the sample effectively to where we can get a good sense of does it glass or does it not. So, I'm going to add a little bit more here too. So this is one of the important tests to do once you have a formulation. And so we're going to see what does a glass look like, what does a not glass look like. I have here, this is pyruvic acid, everybody's favorite. And so if we want to find out what glass is, forgive me, I don't have tongs, so I'm going to try and do Dr. C using a pair of scissors. But what we can do is we can stick it in the liquid nitrogen and let it freeze, and we'll be able to see what a glass looks like. By the way, should pyruvic acid glass or not glass? Glass? That sounds right to me. Does anyone think differently? No? Okay, that should be more or less good. So take a look at it. I think this is helpful. So if you can see, and I'm just sort of gonna, I'm gonna go back to the other side. So take a look. You can see there are cracks in it, but they're only cracks. You can actually, I mean, you can still kind of see through it. Sorry, the water condensation gets in the way. So you see, hopefully that's good. I don't know if I should pull it to the camera, but yeah, you can see what that looks like. And of course it's cold, so water's condensing on it. So this is, yes, this is what a glass looks like. And so, yeah, so that's what we're looking for when we're formulating hyperpolarized compounds. And it makes sense. I mean, our common everyday experiences of glass are that they're transparent, like that glass window over there. So, you know, glass is not a misnomer in that sense. I mean, that's the thing. You know, if it's perfectly homogeneous, there are very few changes in refractive index, which means that light should pass right through it. So, but of course, keep in mind that there are cracks in this thing that we see. So, okay, here's water. Let's see if water glasses. Does anyone think it's going to glass? Does anyone think it's not going to glass? You don't think it's going to glass? Why?
I don't know.
Right. Yeah. That's right. We said crystallization is bad, right? Well, let's see in a second here.
All of these are there under the concrete. So here's
And then we'll see if the glasses are not. All right, take a look. This is what frozen water looks like. Ice. So you can see the difference, right? So this does not look very, very clear. I mean, maybe a little bit, but still, it's cloudy in color. So that everyone can see it, right? You're not going to call me out on any of this. So yeah, as we know, water crystallizes, forms a nice lattice. And so that's one of the problems with using water as a solvent, is that if we don't have the glassing agents in it, you know, that's what happens. DMSO, all right. DMSO, here's one of our glassing agents. Do you think it's going to glass or not glass?
I hope so.
Glass? Yeah, that's right. Yeah, we said DMSO is a glassing agent, right? It's what we use for cell culture, all that stuff. Let's check and see. You know, just making sure that this thing freezes all the way. You may want to. Maybe we should. Let's pull it this way. Maybe we should kind of congregate more to this side of the room if we can. And then we'll get to see if DMSO glasses. All right, take a look at this. You think that's glassy? You think it glass? Kind of. Interestingly, this kind of actually surprised me when I first saw it, but you can see actually there's some stuff in there. And in fact, actually, as it warms up, it starts to get cloudy. See, now it's all pretty cloudy. That's not, it doesn't glass, actually. However, it works well as a glassing agent when it's in water. And in fact, I've noticed that if you start dissolving stuff in DMSO, it actually starts glassing. A lot of the preps, or at least a few of the preps that we have, are a compound in DMSO. I think one of the, wait, hey Colin, is DHA? Is that DMSO? Or is that DM? Oh, shoot. Okay. Anyway, I think there are some preps that are in DMSO, and they do glass. So in fact, you can almost think of your hyperpolar, your C13 agent as the glassing agent for DMSO. I mean, so anyway, you know, it doesn't quite glass, and I don't know. You might be able to change some things in order to get it to glass, but I think it sort of illustrates the point that, you know, it all depends on the formulation. So, any questions so far? That's on any questions on identifying a good glass and all that fun stuff? All right. I don't plan on taking the full hour, and I think we're hopefully 15 minutes in. I'm not sure. But, what I want to do is I want to hand out this. This is a handy dandy hyperpolarized agent formulation flowchart that I put together a while ago. I showed some of this in the slides too. This is as best as I could do, to basically put together an outline of the different parts of of the thought process of what goes into your into formulation. Again, we said there's a lot of educated guessing in this. So you look up your compound, you identify certain properties it has, then you can follow this sort of nice flow chart and ask, basically, try different things. And the thing is, there can be multiple paths here. You can try all kinds of different preps, as we're going to demonstrate right now. So one of the compounds that I think was published on in 2011, actually by our group and also the Brindle group, is what's known as it's ascorbic acid. We know it is vitamin C. It's very important for redox. So the big idea was to formulate it as a hyperpolarized agent. I think it works as a nice compound. So let's say I was lazy and I didn't do a lot of research. But I know maybe a few things about vitamin C. First of all, let's see. So, okay, vitamin C. We know vitamins and minerals, people usually say like they're fat soluble or water soluble. Does anyone know, is vitamin C fat soluble or water soluble? Water soluble, that's right. So that means we should be able to dissolve it in water, right? Okay, so what we can do then is we can do a little bit of, we can test that. So let's say, it's before 2011. I've just come up with the brilliant idea of hyperpolarizing ascorbic acid before anybody else. And I'm really excited to do this, but, I have no idea how to formulate it. And I don't know. Let's say, we're breaking new ground here. So let's find out what we got to do to get this thing into a good hyperpolarized formulation. I'm going to try and, again, this is the C12 compound. As I said, you can get a lot of mileage out of this stuff. So let's weigh out some. And I strongly encourage, taking lots of notes. So, okay, we've got, 276. I'll just kind of try and keep notes here as well. This is what, I'm going to round a little bit, but this is 278 milligrams of ascorbic acid. Okay, here, let's add some water and try to get it in. I'm going to cheat a little bit. I sort of have notes on, about how much this should take, so. Sorry, may I stick by here? I need one of these guys. So I'm basically I'm gonna start adding water until it dissolves. I've done this before, so it should be around 700, hopefully. But this is basically, let's try dissolving it in water. Okay, we've got 700. By the way, as I do this, the best way of doing this is to weigh it out, even when you add the solvents. It makes it the most reproducible. So if you don't add the volume that you think you added, you won't be scratching your head later when you can't reproduce it. Make sense? Mix this all up. A note as well, you can add some heat to get things in the solution, but you have to be careful because remember that can change your compound stability, right? It can start to react more when it gets hot. Okay. So I look at this. It's not quite in there. I'm not really going to heat it too much. Let's add a little bit of extra. Let's add another 200 microliters here. Let's see if we can. Where's my tips? Here we go. Let's see if we can get this dissolved. So far so good. We're on our way. No one knows that we've got this cool idea of polarizing ascorbic acid. Still not quite going in. You can still see like all the, there's like all this particulate stuff. Try another 200 here. Maybe another 300, why not? These notes are old, but not so good. And again, we want to just try to get this stuff as concentrated as possible to start. So as I said, that helps our glassing, it helps our polarization, generally speaking. Well, you know what, I'm going to be mean and bad, I'm just going to heat it a little bit. Still a little stuff up top, but generally I've gotten it all in solution here. It's more or less resolved. That's fine. Good enough to move on. Should be fairly concentrated at least. Alright, so we've got it in water. Let's check the glassing. What time is it right now?
It's about 2:30.
2:30. Glassing. Move up next to this, take a while. Not the best pair with Actually, would you mind that I want you to get like nervous. Alright. Ascorbic acid and water. There's a glass. Yes, no? No, definitely not. That looks kind of cloudy and nasty. So, okay, so what should we do?
Add glassing agent?
Add a glassing agent. That sounds great. Oh, that's fantastic. Thank you. That's a lot better. Okay, what's our favorite glassing agent? Let's add, yeah, I agree with that. Let's add glycerol. So let's see, we added 1 ml of water. So let's add a ml of glycerol. Just to work with it better, I'm going to cut the tip off here because it's a very viscous liquid, as I mentioned previously. So take some glycerol. This is all stuff, so I don't think anything's going to mind. Okay, 1 ml. And again, it's always best to weigh this stuff out so you know exactly how much you're adding. It's much more reproducible that way. Especially with things that are viscous like glycerol, it's tough to be very accurate with the with the volume. So, this is the best way to do that. We need to try to heat this up so it's going to dissolve. If I were really trying to get this concentrated, I probably wouldn't start with the 50% at all. I'd probably start with, I don't know, maybe 20%, 30%, something like that. This stuff's still a little cold, so. And sorry, I'm breaking the rules. I mean, it's up to you. You know, if you want to risk your compound breaking down, you can eat it. Put some more liquid nitrogen. And let's see how the glycerol changes things. Okay, let's see if the glasses. I think I mentioned last time, we also use liquid nitrogen, particularly when you're loading a something into the polarizer that's greater than 50 microliters. Say 50 microliters of green, just so it doesn't spill. So if you ever find you need to do that, you can grab me or someone who has a lot of experience with that. Okay. All right. There we go. Take a look at this. It's a lot different, right? You can see that's it's a nice glass. Yeah. Okay, great. So we've got a formulation. Actually, what's interesting is take a look at it now. It's actually getting cloudy as it warms up. So when it gets to a certain temperature, things can move around enough to where you lose the glass. Now it's formed a crystalline structure. So, but that's okay. It doesn't matter as long as it's a glass once it's frozen. It doesn't matter. It's not going to warm up until the dissolution, and by that point it's fully polarized and ready to eject, right? So anyway, so that's great. Now what we might do is we might calculate how much our final concentration is in this prep. So I added 1,000 microliters of water. I added 1,000 microliters of glycerol. I can look up the molecular weight of this. Usually it's on the bottle here. It's 176 grams per mole, so I can find out how many millimoles I have. 278 divided by, 176? Let's do this quickly, 176. I have 1.57, let's say 1.58 millimoles of vitamin C. And that's dissolved in 2,000 microliters. You can also add in this volume, especially if it's very concentrated. What's interesting is that the compound itself can add volume. So you usually treat the milligrams like microliters. That's normally what I do, more just to sort of estimate. I don't know, in this case, let's just use this 2,000 microliters. So if I divide this is millimoles. If I divide it by milliliters, divide it by 2 mils that it's dissolved in, you should get molar concentration. We get that we're at 790 millimolar, which, not great. Probably not going to polarize too well. So at this point, I might sort of get frustrated, throw up my hands, give up. Well, polarizing ascorbic acid was a stupid idea anyway. Whatever. It wasn't that biologically relevant to begin with. I don't know. I can make excuses. But if I look in the literature, this is where knowing the compound can help a lot. One of the subtleties to ascorbic acid is that you can form a salt with it. So it actually has an ionizable group. And it has one ionizable group that can be deprotonated. Pretty sure that's the case. So if we have a group on it that can be deprotonated, this is the acid form, we can form the salt by adding one equivalent of base. So let's start over and we'll make one more prep, and I think we can call it a day, because we could probably stay here until the wee hours of the evening and just mixing and matching up. See how many compounds we have up here in solvents, and you could exercise some restraint, I suppose. Okay, let's start a new one. Now I've got 147. Yeah, kind of quick notes here. 147 milligrams. Let's calculate the millimoles of that again. 147 divided by the molecular weight is 176. That's 0.835 millimoles. So I happen to have this 10 molar NaOH here. You can get it more concentrated. You get it actually close to 19 molar, but it's viscous, hard to work with. So if you dilute it to 10 molar, you gotta be careful with this, by the way. It's a lot easier to work with. So let's see. So 10 millimoles per milliliter. If I divide my millimoles by this, divide by 10, I should get the milliliters. Okay, I need 82.5 microliters of 10 molar. Great. Great. So let's grab, sorry, I'm going to need to sneak through here again. 82.5. Any questions up to this point? Does this sort of make sense? I mean, a lot of it just kind of gets in check. Okay. Again, I would weigh this out. I just want to reiterate that, just to give myself an excuse for my laziness and not measure it out now. But this stuff's a little old. Let's be careful. Okay. Yeah, it's a little old. Sure. But that's okay. This is a good one. Don't use this stuff when you're actually making a good cut. Make some fresh stuff. But it'll work well for the purposes. Okay. No, I'm not going to get out. Sorry. Right. So it's even a small volume added means that this stuff is dissolving pretty well. So the other thing is it's kind of warm. It's a very it's a sort of exothermic reaction. So now I'm going to add, just to get it all in, I'm going to add a little extra of this. Let's add another like 40 microliters. How about that? Of just water. Adding water. Get all this in. Just a little more too. Wondering if the concentration's off, or maybe I zeroed this with the cap on it. Yeah, that's right. See if this will. So no more particulates in here, and we got a really nice orange color. Pretty cool, huh? All right. Hey, let's find out if your glasses. But by the way, does anyone think it's gonna last? No? Yes? Wow. Glad your audience. So, I mean, we can think about it a little bit. It's in water, right? So water tends to crystallize. But we also just formed the salt of ascorbic acid. So, I'm familiar with, freezing point depression? So what salts do is they disrupt formation of crystal structure. So these two things combined mean that it's difficult to tell, but you can see it actually it glasses. In fact, most salts glass pretty well. I think for that reason. So the salts are basically, you have these ionic species that are interacting with the water as it's trying to crystallize them. They actually glass pretty nicely. They're glassing effectively. So great. So that's awesome. So let me see. I have to remember what I added here. I also added 40 microliters of the NaOH. I added 40 microliters of the H2O. Let's calculate our concentration here. I'm also going to include the 147 milligrams. I'm going to call that microliters just to sort of estimate how much volume the ascorbic acid is added to the thing. So let's see. My total volume is going to be 147 plus 83.5 plus 40 plus 40, which is 210. So my total volume, I'm guessing, is about 310 microliters. If I take my 0.835 millimoles and divide by milliliters, which is 0.31, I'm now at a concentration of 2.7 molar. So that's a lot better than the glycerol water. So that's great. Now, if this thing is, depending on the pH of this thing, salts are generally neutral at both times. I don't know. There could be concerns with stability and all that. I'd probably have to polarize it and see, or put it in an NMR spectrometer. Maybe put it in a DMSO or some solvent and do a measurement on it. But anyway, so you can see we just did 2 preps. They both blast at very different concentrations. The thing we didn't do is we didn't test radical solubilities in this, but that would be the next step. Then, of course, as you're polarizing with your C15 compound, you can start, adding gadolinium and playing with the radical concentration too to see how those affect your building. That's it from me. Does anyone have any questions relating to prep making? Awesome. Well then, I'll let you go.